Okay, my name is Kiran,
And I'm Horace.
and we're going to be talking about adapting credit card fraud detection techniques for automobile insurance claim fraud.
So I know that's a mouthful, but we'll quickly go over what we'll be discussing today. So first, we're going to talk about older papers and show you where we really got our inspiration from. And then we'll take a deeper dive into our method, what worked, what didn't work, how we improved it. And then finally, we'll finish off with the results and the conclusion.
So we're going to go ahead and start on some papers that we interpolated. The first one is Credit Card Fraud Detection Using ADA Boost in Majority Voting. This paper is by Ramasar et al. 2018. This paper focused on aggregating several different machine learning algorithms to classify credit card fraud. And we chose this paper because credit card fraud has very similar attributes to insurance fraud, and we want to try to apply the same method to be able to classify insurance fraud. The second paper we're going to talk about is a cost minimization approach to automobile insurance fraud detection by Randawa et al. 2023. And this paper focuses on logistic regression machine learning algorithms for classification.
All right, so now that we know where we got this inspiration from, we'll take a deeper dive into what we did and how we did it. So first, let's talk about our data set. And as you can see right off the bat, our data was very highly imbalanced with, I think we had about 15,000 data points and only 6% of them were fraud. And then along with this, we had 33 features with the fraud found P being our label for determining whether something was fraud or not. So like Kiran was talking about with the credit card fraud, that is the main approach we took for vehicle or for determining fraud within vehicle claim insurance. And what we used was logistic regression, decision trees, random forest, and naive Bayes. And we undersampled the majority class and used ADA boost with majority voting to determine whether something was fraud or not.
So we're going to dive a little bit more into those machine learning models that we used. The first one is logistic regression, and we chose this one because of that second paper. That second paper really emphasized this model being good at drawing a good sigmoid decision boundary between the features for insurance claim fraud. The second one is naive Bayes classifier, and this classifier uses prior probabilities of each feature, which are assumed to be independent, to calculate the posterior probabilities. The next one is decision trees, which calculates the probabilities of classification based on the probabilities of each feature. And the last one is the random forest classifier, which uses several different decision trees on subset of the data and then votes on the decisions made based on classification.
So with all four of those models, like I mentioned earlier, we use AdaBoost. But what really is AdaBoost? AdaBoost is a machine learning ensemble technique designed to improve the performance of weak classifiers. And there's three main parts to it. The first is sequential training. So weak classifiers are trained one after another. So each successive classifier focuses on correcting the mistakes that the previous ones made. Second, we have weight assignment. And AdaBoost assigns weights to training examples, emphasizing harder to classify instances. So something that was misclassified will receive a higher weight so that we address it with like the next instance. Finally, we have weighted voting. After training, each weak classifier is given a weight based on its accuracy, and the final prediction is a weighted majority vote of the individual classifier's predictions.
Now we're going to talk about feature selection. We noticed that there were many features that we did not believe contributed to the classification of fraud. Some of these features include day of week, year, day of week claimed, month claimed, week of month claimed, and days policy accident. We decided that these features were either irrelevant or 99% one statistic, which we thought made all of these features noise.
So along with that, we had many categorical features that our models could not handle. So for example, number of cars. The options were one vehicle, two vehicles, three to four, five to eight, and more than eight. And to make things easier for our model to understand and have like for it to be easier to train on, we mapped those categorical values to numbers. So like I said, with number of cars, what we had before, we mapped those values to 1, 2, 3, 4, 5, which made it easier for our four models to train on.
Now we're going to talk about the results of this experiment. So we had several different machine learning models that we used in conjunction with each other, alone, etc. And we had to decide which model was classified the best. So the score that we use the best is MCC score, which is the Matthews correlation coefficient. This is a measure that evaluates the quality of binary classifications despite the dataset being imbalanced.
All right, so this is kind of like the bulk of our result. And as you can see, we recorded the MCC for a wide variety of combinations of the models. And we did it with the noisy features and after we removed the noisy features. And I highlighted the best instance in green, and that was logistic regression, decision tree, and naive Bayes. Something else that I wanted to point out was the instance right below it, logistic regression, random forest, and naive Bayes. That was the only instance where after we removed the noise, the MCC score actually went down.
So let's evaluate the performance of this best model. As we can see, the graph on the left is the ROC curve before we removed the noisy features, and on the right is after we did so. The AUC score on the left is 0.086, and on the right is 0.88. So there was a slight performance uptake in AUC, but as you can see with the precision recall curves, there was a significant uptake in the classification of the minority class. And this is emphasized in precision and recall statistics because of the imbalanced class. The ROC curves did not really accurately display this, but looking at these two graphs, you can see the difference in the right one.
So here we have our confusion matrix, and as you can see, our true negatives is insanely high, 0.93, which may lead you to think that our model was amazing, which I mean, obviously we would hope for that. But as you can see, our false negative rate at 0.05 is also pretty high. What that means is 5% of the time we let fraud sneak through the door. So someone made a claim for a vehicle insurance, and they were it turned out to be fraud, and we weren't able to detect it.
So we're going to go ahead and analyze why that might have happened by instead looking at holes in our intuition by comparing it with the credit card fraud case. So what went wrong? First of all, class imbalance. A lot of difficulties from our classification stem from the fact that real-world instances of fraudulent claims are hard to obtain. So our data set was very imbalanced. As it makes sense, a lot of these fraudulent claims are hard. A lot of data sets with fraudulent claims are hard to find. So our data set contained 6% fraudulent claims. That made it very difficult for our models to be trained. The next one is the nature of the insurance fraud problem. Our original model was made for credit card fraud, and the nature of these two problems, insurance fraud versus credit card fraud, are very different. Some of the reasons that this could have happened, credit card fraud has behavior of transactions, which includes statistics like frequency, quantity, and history. These don't really apply to insurance fraud because insurance claims contains more about features about the context of the alleged occurrence, and definitely not about frequency or quantity or history. The last thing is temporal patterns. Like I mentioned before, insurance fraud claims are not likely to happen as often, especially from repeated offenders. And this is different from credit card fraud, which is how they identify credit card fraud, which is by credit card fraud happening in a small window of time by the same people. This does not happen with insurance fraud.
Thank y'all for listening. We hope y'all enjoyed.